Oh, okay. All right. So today I'll be giving a talk that will be describing how my co-authors and I have been using sulfur isotope measurements in a variety of lunar materials in order to identify whether there are multiple distinct sulfur reservoirs on the moon. And today my goal is to convince you that there are, and I also want to do that we can now use high precision quadruple sulfur isotope measurements and in situ triple sulfur isotope measurements in order to uncover previously unknown processes that likely occurred throughout the moon's evolution. Now, I've been very fascinated and have specialized in sulfur isotopes, particularly because sulfur has 4 stable isotopes. Depending on your pressure and temperature conditions, it exists as a siderophile, chalcophile, or volatile element. In the rock record, it exists as in different oxidation states from -2 to +6. And what's most useful for my work is that I can use measurements of the ratios of the isotopes in order to evaluate and identify evolutionary processes that fractionate the isotopes in ways that are both mass dependent and mass independent. And ultimately, in my work, I combine all of that information in order to constrain the various processes that are associated with processing sulfur on the lunar surface, within the lunar interior, and also within a lunar atmosphere. Now, when we consider the earliest evolution of Earth and Mars, we know that there are there's a significant amount of sulfur outgassing from volcanoes, and these gaseous sulfur molecules are interacting with ultraviolet light. And this interaction results in a distinct fingerprint or a distinct isotopic composition associated with atmospheric chemistry. Now, when we consider the moon's evolution, there are 4 main stages of, say, giant moon forming impact, differentiation, volcanism, and even soil maturation. What's key is that each of these 4 main stages results in the production of sulfur-bearing gases in the presence of sunlight. And so we have then been questioning whether we can observe any sort of evidence that there has been atmospheric volatile processing on the moon that is similar to events that were occurring on early Earth and Mars. Now, when we established a baseline for the sulfur isotope composition of the moon, what we initially observed was that the delta 34S composition, that mass-dependent tracer, was relatively homogeneous but fractionated from the assumed origin of 0, and that has been attributed to a relic of magma ocean crystallization. But what's even more interesting about this data set is that the cap delta 33S values, that's on the y-axis, the mass-independent tracer, is exhibiting more heterogeneity in those values than what we would expect for a well-mixed lunar mantle. And so with that, we've decided, well, if this is more heterogeneous, perhaps there are multiple lunar sources that are contributing to the sulfur erupted among the basalts. And so we then decided to investigate the nature of sulfur in soils. And what I would call the fingerprint number 1 is this process of soil maturation, where we find that the delta 34S values in lunar soils are strongly fractionated toward positive values that we ultimately attribute to the process of atmospheric escape once a micrometeorite bombards these soils and emits sulfur gas into the atmosphere. But what was even more exciting was that one of the soils, 75081, exhibited strong mass-independent fractionation that we ultimately were able to attribute to the interaction of UV while that sulfur was in the tenuous lunar atmosphere. And so what we see in this plot is of sulfur isotopes for these lunar soils is that as we sieve the soil grains and we go from large grains to small grains, we see a surface to volume ratio at play, and we can characterize the nature of the sulfur-bearing gas in the lunar atmosphere that is condensing on the lunar soils. Now, it's in one way we could say, oh, perhaps this is contributing to the compositions or the variability that we see in lunar basalts, but this is a process that is relatively young, and even though the constituents of the soils are old. And so although this is a fingerprint, it's likely not what is contributing to the variability that we see in lunar basalts. So we then, after recognizing that the lunar soils are exhibiting mass-independent fractionation, we were then questioning whether, say, pyroclastic glass beads also exhibited a similar feature of atmospheric chemistry, say from the volcanic cloud, associated with that eruption. And instead of seeing a correlation between the sieve grain size fractions, we see no change in the cap delta 33s between the largest size fraction and the smallest size fraction, even though the delta 34s values are fractionated, which is ultimately attributed to a fractionation associated with volcanic degassing. Now, given that the values of the cap delta 33s and the orange glass beads are anomalous, and they don't change between the largest size fractions and the smallest size fractions, and what we ultimately were able to, or what we believe or hypothesize is the reason for this, is that the lunar mantle has a distinct mass-independent sulfur component that is being erupted with these pyroclastic glass beads. And although there is evidence of sulfur gassing into these glass beads, it may contribute to this cap delta 33s variability, but it's possible. I would say that it's not able to explain all of the sieve size fractions and what we are observing. But what we find is that even though we do see this anomalous signature in the orange glass beads, and we're making a hypothesis that we have an exotic sulfur source erupting from the lunar mantle, we are left questioning, how do you take an atmospheric component and deliver it to the lunar mantle without, say, plate tectonics? So we decided to investigate this problem a bit further and determine whether we can find evidence of mass-independent fractionation associated with endogenous sulfur. And so we analyzed individual sulfides from regolith particles from 73002, and we targeted regolith particles that were associated with the lithologies that would suggest that these sulfides are endogenous. And what we find is that some of the sulfides have the largest mass-independent fractionation signatures ever recorded in lunar materials. And so this is ultimately unambiguous evidence for source heterogeneity in the lunar mantle.
2 minutes.
2 minutes. Okay. And although this is unambiguous, we're still left wondering, how do we establish this exotic signature erupted among lunar volcanic rocks? So we've questioned whether it's a nucleosynthetic anomaly, perhaps it's delivered by some large impactor, perhaps there is some sort of crude or early primitive crustal recycling, but it's difficult to reconcile that. It's difficult to determine that with the data that we do have. Now, what's interesting is that it's loading. Okay. What's interesting is that my student and postdoc, we've been working on in situ sulfur isotope analyses associated with Martian meteorites. And what we find is that even among the most primitive Martian meteorites, we are finding these anomalies, mass-independent fractionation, and it shows an increase in magnitude of mass-independent fractionation as you go to the most enriched Martian meteorites. And through quantitative modeling, what we find is that we're able to model this, the data that hopefully will show up with the process of magma ocean crystallization as well as exchange between the Martian atmosphere and the Martian interior. And so it's possible that we can invoke a similar process for the lunar mantle, but we do need additional analyses. And so through our through survey and through solar system workings, we have plans to analyze a variety of lunar materials to get at what the potential or how much heterogeneity in sulfur there is in the lunar mantle.